Greetings, AP Chem. Today we're going to be talking about rates of chemical reactions. So all of Unit 7, as far as the way I teach it, deals with what we talk about as chemical kinetics. And we talked about in the first part of this reaction mechanisms with the steps of how things actually happen. But honestly, the focus of the kinetics unit is really on reaction rates and rate laws and integrated rate laws and all that kind of stuff. So our big focus essentially is on how fast does a chemical reaction happen? What can I do to make it happen faster? And how can I describe what's going on in that process as I'm taking a look at it? So do changing the concentration of reactants affect it? And if so, how? And that's what we're going to kind of dig into. So the first thing you need to understand is what the heck is a reaction rate? So a reaction rate is how fast a chemical reaction happens. And in the case of our reactions, I would say like 95% of the time, they are going to be measured in a change in concentration over time. So typically that's going to be in like molar per second or moles per liter per second or millimoles per minute or something along those lines. Once in a blue moon, you might see a pressure value in there, but I honestly think that the majority of the time you're going to be seeing a concentration value in there. So really be aware and be comfortable that if I have a molar in my numerator, that is exactly the same as having moles over liters and then a time component. Or you could see moles and then like liters to the -1, seconds to the -1 for your units as you go along with that. So essentially what a rate does is it measures how the concentration of your reactants and your products change as time progresses. And what I will say is that the vast majority of the time, chemical reactions happen fastest right at the beginning. And then as time progresses, as we tend to run out of things, they slow down. So you will see your biggest changes in concentration at the beginning, and then it will kind of taper off from that point on. If you start your process with all reactants, the concentration of your reactants are going to go down. And at the opposite time, your products are going to go up. And the biggest thing that you need to be aware of is that the change that happens, whether it's a positive increase in your products or a negative decrease in your reactants, is that the initial amounts are set by how much you have available for your actual process. But the change that we actually see is relative to the mole ratio that we have been talking about forever in this class. So I'm going to go through an example here with some Alka-Seltzer. And I think you guys have seen how the tablet works, but I want to just kind of talk to you a little bit about this. So I'm going to play this super riveting video here and just be ready for it. I told you it was exciting. Okay, so a couple things to note there. When I set the experiment up, what I did was I took the initial weight with the beaker on the balance as well as the Alka-Seltzer tablet, so that when I added the Alka-Seltzer tablet back in, that would undergo its chemical reaction, and then you would see a mass change, but that mass change wasn't from the tablet, being on there or off of there or whatever. So a couple of things I want you to note. When I add that tablet in there at the beginning, you'll see the reaction kind of start to happen, and then it gets very vigorous, and then it tapers off. So like I said, your reactions tend to be most quickly changing their concentrations as your reaction starts, and then it kind of tapers off from that point. The reaction that's actually happening in an Alka-Seltzer tablet is this one here. So what it is it's baking soda, which is sodium bicarbonate, and citric acid. And so what happens is they are in their dry form and they are in the tablet together with a little bit of aspirin. It's designed to help a tummy or a hangover. And then it takes 3 baking sodas to neutralize and react with one of these citric acids, and they're in their solid form. And what happens is when I bring them into the water, they dissolve and then they start to react. So they have to dissolve, which is why it kind of took just a minute for that to get going, and then it really took off for our reaction. They make something called sodium citrate. They make 3 moles of carbon dioxide and 3 moles of liquid water. And so the effervescence or bubbling that you're seeing there is the carbon dioxide leaving. And so in theory, everything is staying in your reaction container from start to finish except for the carbon dioxide. So this mass change that you guys are seeing here on the balance, that is carbon dioxide leaving. And that's what we're going to take a look at here. But like I said, what's important in this case is going to be these mole ratios here of 3, 1, 1, 3, 3. And we'll see that in just a second. Oh, we don't want that. You've seen that already. Okay, so here's what I did. I took the data, not from that reaction that was just in the video, but from a previous trial of that experiment that I ran. And what I did was over time, so as the seconds progressed, I measured the mass change that happened with the carbon dioxide. So what I did was I took that number of grams of CO2 that left over, I think it was a 90-second period. And then what I did was I think we skip, if you see here, the 10-second mark because there's not a lot of change. It happens right at the beginning. But what I did was I measured the CO2 production. And then I turned that into moles and I graphed it. So these blue dots on this graph here indicate my production of CO2 over time. So what you can see is that I have kind of a very rapid rise in my CO2 moles, and then it flattens out, which is kind of what I had mentioned before. So with our rates, it's most aggressive kind of right at the beginning, and then we kind of flatline towards the end there. If you notice, this is a positive growth here because CO2 is a product, and so I'm creating carbon dioxide, so it's going up in its concentration. This graph also shows me what is happening with my moles of baking soda, which are these guys right here, and my moles of citric acid, which are these guys here. But like I said, what's really important here is going to be the ratio. So if you look, I start off at a 0.022 moles of baking soda that are in my tablet. Now I got that from using the actual data on the back of the package to figure that out. But what's important here is going to be the shape. So if you look at the shape of the carbon dioxide, the shape of the baking soda is essentially mirrored in this graph. And that is because of a couple things. One, the concentration or the number of moles of baking soda are going down because it's a reactant. Two, they have the same rough shape and rate of change here because of the 3 with the coefficient. So what this means is that if I have 3 moles of baking soda reacting, I am going to produce 3 moles of CO2. So since their mole ratio is equal, their graph shape should be about the same. And if I'd want to calculate the rate, what I could do is I could take my moles in theory per liter and then divide them by the time, and that would get my rate. And so what will happen is that my rate for my CO2 production should be the same as the decrease in the concentration of my baking soda because they have that same mole ratio. Now, if you look at citric acid here, the other reactant, citric acid's line here looks almost linear compared to that of carbon dioxide. So you can see the very dramatic drop for the baking soda, dramatic rise for the carbon dioxide. But if you look at the citric acid line right here, like I said, it looks almost linear. And that is because of the coefficient of 1 in front of my citric acid. So what's going to happen is that I'm only going to use up 1 mole of citric acid for every 3 moles of baking soda that gets used up. So if you look at this, you're going to see a much more dramatic decrease overall in the number of moles for baking soda because it gets used up 3 times as fast versus the citric acid, which is being used up at a rate 1/3 that of baking soda. Here's just another look at this. I think it's maybe a little easier to see without the dots. So if we look at the lines, you can really pretty clearly see that the baking soda and the CO2 have pretty much the same shape. And then the citric acid drops at a much slower rate because it's got that coefficient of 1. Okay, so when we talk about rates, that's just kind of something to keep in mind is that, like, if I want to look at this, my rate of production for the sodium citrate should be almost like a mirror of the citric acid because they have coefficients of 1, and the H2O would be a mirror of the carbon dioxide for that reason. So just something to kind of keep in mind. There are a bunch of things that can potentially change a rate. So rates change when the number of collisions change, which you know already. They have to be oriented correctly. They need to hit hard enough, and they actually have to hit in the first place. And so when they hit in that correct orientation with the correct energy, they overcome our activation energy. So there are some things that we can do to actually make our rates change. One of them is change the quantity of reactant. So if I have a higher concentration or a higher pressure of a gas, generally I can make that reaction happen because there's just more particles around to smash into each other. So hopefully that makes sense to you. Temperature can also increase your rate. What'll happen is when we have a temperature that's warmer, the molecules move around faster. They collide with the container or with other neighbors harder, and they collide more frequently and with more force. And so in general, a higher temperature means a higher reaction rate. And so we'll get up to that flat part a little bit faster. Not necessarily something they're maybe going to ask you on the exam, but if you increase surface area, that also increases reaction as well because there's more places for collisions to happen. And then lastly, our catalysts, which we know about. So a catalyst decreases the activation energy, and then it makes it easier for those molecules to have enough energy to have a successful collision. On the opposite side of that is something called an inhibitor. An inhibitor is something that slows down a chemical reaction and makes it so it's difficult for that actual process to happen in the first place. So that's just your brief intro to rates. What we're going to talk about now is how that rate is affected by changing specifically reactant quantities. So if I change the concentration of one thing, what does it do to my overall reaction? And that's what we're getting into next. So if you have any questions, please let me know. Otherwise, we'll move on to the next part of 7.2.